Is generative AI decidable? This question may sound like a conundrum. Unraveling it, however, brings us deeper into the fascinating world of computation, logic, and artificial intelligence. To make sense of it, we first need to grasp what is meant by decidable in computational terms. Decidability, in computational theory, refers to whether a problem can be definitively solved. More specifically, a problem is considered decidable if there exists a precise algorithm that can produce a correct yes or no answer for every instance of the problem within a finite time frame. This concept is primarily applicable to decision problems, which result in a binary outcome, true or false. Now shifting our focus to generative AI. This term encompasses algorithms and models, such as generative adversarial networks, transformers, or variational autoencoders. These models have the astonishing ability to create new content, be it images, text, music, and so on, that mirrors the content they were trained on. But how does the question of decidability fit into the picture of generative AI? One way to interpret this question is to ask whether, given a specific input or set of conditions, the AI will invariably produce a specific output. Many generative AI models incorporate elements of randomness or are influenced by non-deterministic factors during training, making the prediction of a specific output for a specific input essentially unpredictable, and thus not decidable in the strict computational sense. Another angle could be whether it's possible to predict or determine the behavior of a generative AI model in all situations, such as whether it will converge during training or how it will extrapolate from its training data. Given the complexity and nonlinearity of many AI models, this is also generally not decidable. The behavior of these models can hinge on numerous factors, including the model's architecture, the dataset, and the training process, making it challenging or even impossible to definitively predict outcomes in all scenarios. If we're asking about the ability of generative AI to solve decidable problems, then the answer is contingent on the specific problem and the design of the AI. BigGraph unveils Decidability.ai, harnessing the power of generative AI to solve specific problems within defined areas. This innovative platform delivers answers with minimal ambiguity, drawing upon its extensive training and tailored capabilities. By adding this new dimension of AI, BigGraph empowers domain users with comprehensive insights and informed decision-making. Turing machines, a central concept in decidability theory, can be represented as graphs. Each state of the machine can be a node, and transitions between states can be represented as edges. This allows studying properties of Turing machines through graph-theoretic tools like reachability analysis, shortest paths, and graph isomorphism. By analyzing the graph structure of a specific problem's Turing machine, we can gain insights into its decidability. For example, cycles in the graph might indicate non-termination, an undecidable problem, while simple linear structures might hint at halting and decidability. Generative AI's unique capabilities transcend the limitations of traditional decidability concepts, opening up new possibilities. Despite their complexity and occasional randomness, generative AI tools still hold immense potential to revolutionize various domains. Understanding and working with these advanced systems presents challenges, but BigGraph AI helps navigate that complexity, empowering domain-specific solutions and unlocking opportunities for growth.